One, two, three. Let's go. So, hello and welcome. You are on a call with Current Continuation, which is a podcast. So, I'm Aus Al-Barghouthi, and this is my colleague Adrian Sampson. And we co-edit the SIGPlan Programming Language Perspective blog, where the PL community contributes blog posts about all kinds of stuff. So, if you haven't seen it, please check it out and maybe even contribute articles. We kind of got bored of text, and we thought we'd change it up with video. So we decided to interview programming language luminaries, and we think it'll be a great resource for the community, both like the PL community itself and CS at large. So that said, our first guest today is Professor Ranjit Jhala, who is a professor at the University of California, San Diego. He received his PhD at UC Berkeley, and before that, he was an undergraduate student at IIT Delhi. He's made seminal contributions to static analysis, verification, programming language design, notably lazy abstraction and liquid types, both of which we'll talk about today. He's received many accolades for his work, including the Robin Milner Young Researcher Award. So Ranjit, thanks for taking the time on a Friday to talk to us.
Well, thank you very much, Aus and Adrian. This is a real pleasure. And
yeah.
Looking forward
Delighted
to
to have you here, Ranjit. I really appreciate you agreeing to do this and be our guinea pig for the first time.
Yeah. We're aspiring podcasters.
Right.
All right. So maybe let's start at the very beginning. Tell us about your undergrad education. Like, where'd you go to college? Why CS? Why not, I don't know, English?
Let's see. So I went to college. Actually, it's funny you should say YCS and not English. I'll tell you why. But I went to college at IIT Delhi, which is, it's one of these sort of five, well, there used to be five, but now there's many more sort of Indian engineering schools. Why CS is, I had a really inspiring computer science teacher in high school. And why not English is kind of, it's interesting because the two things this guy did, his name was Abhijit Sharkar. He was just very inspiring. Anyway, so I love the subject, because I really, everything this guy taught him, he was really great. But the two things he taught were CS and drama. So he was he used to teach computer science and he used to sort of, and he was also a playwright and he would, but anyway, I never got anywhere with the drama, but anyway, so that's why. So I really, and same, I mean, like with many other people, I think my dad, when I was like 10 years old, he used to be, I grew up in India and he had a trip abroad and the thing he brought back, this was like in 1985, I want to say, this tiny little thing called Sinclair Spectrum, which had 48 kilobytes of memory, right? And you sort of hook it up to your TV. And anyways, I guess that's where I caught the bug. I really sort of enjoyed learning to program. And then this teacher was, really inspiring. And so then I got into IIT and, I wanted to, study CS. It was pretty fun.
Do you do any programming on the spectrum?
I did, like many other people, the first program I wrote, I vividly remember it was 10 print hello, 20 go to 10. And then my brothers and I would roll off our chairs, once we sort of hit run or whatever. But then we would do this thing where, I mean, back in the day, you could get these like books, and these books would, they would just have like long source dumps, right? And then we would spend all afternoon just painstakingly typing. At the time, I didn't know what those things meant. We were just like typing the characters in one by one. And then, 2 hours of that, and then we'd get to play that game for like 5 minutes. And my mom would say, okay, that's it, time is up. And she'd unplug. But yeah, I did do a bit of programming. Very, very little. But yeah, it was.
Typing counts as programming, I guess.
I think so.
Yeah. Sure. So we wanted to keep on going chronologically here too. So you majored in CS. What made you want to try grad school? Like, what made that seem like a good idea, despite all the obvious downsides?
That's a good question. I should think about it. I feel like I might be rehashing my, what do you call it? Like a statement of purpose. Again, I was very fortunate because as an undergrad, I had a bunch of really inspiring sort of professors. And so I just, like the gentleman Sanjeeva Prasad, he taught me logic. In my, I think it was, what do you call it? In my second year, we had to take like an intro to logic class. And Yeah, he was just very charismatic, and I just found the material really interesting. And I mean, the thing I remember, he may have forgotten this, but I remember this thing where we had an exam, and there was this, we sort of read this thing, and it says a string is a map from the natural numbers to the set of characters, and I was like, say what now? I mean, so yeah, so I guess I saw that, and then we sort of learned about computability and undecidability and all these things. So I just didn't really feel ready to get a real job. And I think the best explanation for why I went to grad school was sort of given to me after the fact by Ben Liblet, who some of you know. And so Ben Liblet likes to say, grad school is the snooze button for real life. And I feel that that really kind of applied to me. I just didn't feel ready quite to, take on real life. And there was all this cool stuff that we were learning about. And I kind of just wanted more of that. So yeah, I think that was it. I didn't have any I beyond that I really didn't, I had no idea what happens after grad school, after you do a PhD. So I just like we'll just like keep doing more of the same.
When you started, were you pretty sure you wanted to do PL stuff, or was it just like, let's just see what there is to offer?
It was so I'd already gotten into, I mean, the thing I like to say, this is the kind of thing that gets you canceled, but PL is not something that's a very well, what shall I say? It's not as universally sort of it's not as universal. It doesn't grab people. It doesn't grab everyone in the same way that say graphics does. Like when I was a child, it was like graphics is amazing. Draw these cool 3D pictures. And then when I was an undergrad, like all my classmates, we all loved graphics and image processing and AI and stuff like that. But there was a very small set of people who liked the sort of the formal, like this logic class. If you polled my there were like I was in a class of, if I recall, about 50 to 60 other undergraduates. They would not be speaking so gushingly about this class as I did, as I am, right? There was this one, and then there was a formal semantics class, right? An undergrad PL class. Again, the same gentleman taught us, Sanjeeva Prasad, and it was lambda calculus. Yeah, so I was pretty hooked. By the time I finished all this, I knew I wanted to do something kind of formal. I also thought I might want to do like algorithms because I did enjoy complexity and algorithms and that sort of stuff too. But yeah, once I got to grad school, it was pretty quick. I mean, so I sort of like formalish things, but I also like to program. And so to me, that was just well then. I mean, PL was it was a very natural home. So yeah, I kind of zoomed in pretty quickly.
So what was it like? Like I guess you went to Berkeley, right? So
Yeah,
directly after undergrad. And what was
yeah.
it like? You show up in Berkeley after completing your undergraduate degree, and then you start working with Hensinger. Is that right? Thomas Hensinger.
Yeah, I started working with Tom. Well, I mean, at the time, I'm trying to remember. I think it was Tom may have forgotten this, but when you show up in Berkeley, I mean, so the thing that you're most thinking about is where am I going to live? Because it's actually at the time it was it's much harder now, but even then it was quite difficult to find an
Well, it's
apartment.
either up the hill or down the hill, no?
Yeah, but then you have to actually like find a place, and there was like we went to
Yeah.
a couple of open houses. Anyways, I was very stressed out about all of that. And the first thing that Tom said to me when I just met him, so I was like, okay, maybe work with Tom, or maybe I'll meet with George Nekula or Alex Aiken. There were several other really fantastic people there. But the first words out of Tom's mouth were, "And have you found a place to live?" And I was like, "Oh my God, he has touched my heart, just by saying this." So yeah, but that's kind of, I mean, what happened is I started in my very first semester. I took a class, I think, with Tom. Tom taught a model checking class, and then I took a class with George Nekula on what was called automated deduction. And yeah, I think these both happened in my first semester, and it wasn't clear, which one I'd end up working, or, if I was going to work with Tom or George. Um, but yeah, I think yeah, they were both fantastic, but Tom, and then yeah, I guess my colleague Rupak was already working with Tom, and
Hmm.
yeah, somehow we ended up. It was somewhat organic, I guess. I ended up working with him pretty quickly.
Yeah, yeah. So we had the discussion about your long collaboration with Rupak. I was when I was a graduate student, reading papers on software model checking. I
Yeah,
didn't know you guys, right? Like I didn't know you and Rupak, and I would see like Ranjit and Rupak, Ranjit and Rupak, and I'm like,
right.
these guys are gods. So so I'm just like curious how you both like. started working together and continued working together afterwards. It feels like it's nice to have a research buddy, right? Like
It is fantastic to have a
yeah,
research buddy. If there's any
yeah,
people who are, eventually going to go to grad school or just beyond, I cannot recommend it highly enough. That was really
yeah.
the highlight. Was how I started working with Rupak. I think, I'm trying to think. I I suspect, I was taking this class with George, and Rupak was in that class. Rupak and I are also from the same city in India, by the
Mm,
way, as it happens. And I remember, I only realized this sort of after the fact, but we used to do kind of trivia contests together when we were in high school. So he was like a year older than me. And I'd
mm.
kind of forgotten this, but then I was like, wait a minute, you were on the Calcutta Boys School team, right? And so there were all these kind of extraneous connections. But I think ultimately it was just that, he was like a year or so older than me, and he was working in Tom's group, and maybe I mean, he was literally my office mate. So he was like literally the desk next to mine was Rupak's. So yeah, and I think Tom, I remember but whenever it was 2001-ish. We took this. Oh, actually, I remember we took this class project, right? I mentioned I took a class. I did this class project with Hensinger, Tom's class, and George's class. We did both our projects together. Yeah, it was just a lot of fun working with him. So,
Yeah.
it just kind of all sort of happened quite organically after that. And I can't recommend it enough because, as I'm sure you and Adrian have sort of seen this yourself, is you have when you have two people working on a thing, it's it's very easy to get for one person to get stuck, and just the other sort of other perspective is like, oh, wait a minute, if you just look at it this way, then it's like, oh yeah, and then it's just 1,000 times faster, and it's just much more fun. So
Right.
yeah, so that's how that happened, and yeah, that was a really lucky. I was very fortunate that that worked out.
Cool. We were all fortunate.
But
Great.
yeah.
It
Um,
sounds great. I was going to ask if Rupak is still available. I could really use a research buddy. It sounds perfect.
He is, yeah, he is, and Rupa kind of knows everything, so he's also, I think his interests were like a huge superset of mine. So it just, it sort of worked out quite well,
Great.
um, to work with him. Hmm.
So we wanted to also ask about the model checking era, what Alice is referring to
Yeah.
here. And could you just start off by telling us what software model checking is? Give your own definition.
Boy, it's been a while.
Feel free to say no if you don't want to.
I could. Let's see, what is software? I mean, I don't want to say something wrong. I'm going to do this weird thing where I'm going to look up my own paper.
Yeah, you've written the survey.
I did, but it was a while ago. I mean, what is software model checking? So let's see. I think um it's also difficult for me to answer this question now because it's a how shall I put it? Around 2000 or so, when I sort of started grad school and all of this, there were there were three sort of very different strands of work going on. So there was sort of and these strands really had different communities. So there were the model checking people, and to the model checking people, a system, a program, piece of hardware, computer system, whatever, is a state transition system. You have a bunch of states, and the states sort of hop from one thing to the other, right? Then and in my head, so there was like Tom, right? Then there was George Necula, who was kind of, he was doing sort of what I'm going to say. He's like the Floyd Hoare, the program logic. He was sort of roughly in the program logic community, right? He done this proof carrying code work, which came right out of the program logic, Floyd Hoare, loop invariants, pre and post conditions, SMT solvers. And then there was Alex Aiken, and Alex Aiken was sort of roughly in the, program analysis. He was doing the stuff where you think of maybe types or set inclusion constraints. You have sort of graph constraints describing. And these were like three completely separate communities. And one of the things that, I mean, I like to think it happened, much because a lot because these guys were at Berkeley and they wrote this big OSQ grant. And, there's a lot of really well-known alum from that, from that particular open source software quality. We would have these sort of weekly lunches where now these three areas are all like smushed together. They've all become a blur, right? In a way that was not really true in 2000. So to answer your question, software model checking, I think, is this view where, well, you start off by, the hardware model, you have sort of states and transitions, and so you want to bring that same view to software. You have a program, And how can you sort of analyze a program if you think of it as a sort of state transition graph? And really, there are two ways you can do it. One is well, you literally sort of try to enumerate all the different states. Think of it as a kind of graph traversal, graph search problem. And I'd say spin and very soft are two kind of notable old examples of this, where they're literally just enumerating states and so on. And the other was the style that sort of we and the slam and all of this came, which borrowed a lot of the ideas from Floyd-Hoare logic and then abstract interpretation and static analysis, where you don't work sort of one state at a time, but you try and build these sort of collections of states and you try to explore regions of states. But still, you're trying to compute a fixed point on this graph where you're trying to explore all the different configurations the machine can be in, right? And I would say broadly speaking, that characterizes how I think of as software model checking. I don't know if Aus may have a more recent
No, yeah,
and nuanced
you
view.
know. That's
Um,
exactly how I think of it.
Feel free to say I'm wrong. It's
Yeah,
been a
yeah.
yeah.
You're partially right.
I'm partially right.
Partial correctness.
Right. Um, right.
Um,
And yeah, I should I always I don't know if I've ever said this story before, but there was a very important moment for me. And this is when I was actually interviewing at UCSD. Because I was like, okay, I thought of myself software model checking. And when I interviewed at UCSD, one of the people I met, he has passed away since, but he's a very well-known sort of programming languages researcher called Joseph Gogan. And Joseph Gogan said, I've always found model checking to be very inelegant. Because this business where you are just like enumerating states one by one, brute force, it just doesn't feel right to me. And he just made this. He wasn't being mean or anything. He was just like making we were having a nice conversation, and it really stuck with me. He's like, you know what, he's kind of right. But anyway, let me give you another of my favorite little anecdotes about this view about model checking and versus say program logics is one of the biggest results in model checking over the 90s. It was a huge deal. Was this notion of what is called symbolic model checking, right? Else will know what I'm talking about. The idea here was, oh, you don't think of exploring the states sort of one state at a time, exploring one by one the different states. You have logical formulas that represent sets of states, and then you use, in this particular case, it was first BDDs and then SAT solvers to sort of let you, say, okay, given this formula that represents a collection of states, what's the set of states in one clock cycle, and so on and so forth, right? Well, the 90s, I mean, at this point, it's kind of obvious in retrospect. This is exactly what Floyd-Hoare logic is. It's Floyd-Hoare logic is symbolic model checking, and where you're using the assertions to represent sets of states, right? And you can call it sort of weakest precondition, strongest put. They were literally the same thing, right? But you're sort of manipulating these sort of sets of states symbolically. But I think just because these communities were largely disjoint, a lot of these kind of connections maybe were not so obvious and explicit.
Yeah,
Yeah.
yeah. I also felt, I mean, I guess I think I started my PhD at the time where they were mushing and everything was just like, what do I use? Like, do I read
Right.
those old interprocedural analysis papers, or do I just use like, the standard Hoare style interprocedural, rule, or like
Right.
the whole thing was a jumble.
Right.
Yeah.
Right.
So it's interesting how things diverge, but then they kind of collapse,
Correct.
and then
Right.
maybe they'll diverge again soon.
Right.
So we'll see. But so I wanted to ask about lazy abstraction, since that was, your, I guess, big result in grad school.
Yeah.
So like, how did that came about? And maybe describe it for us, because it's a very elegant idea.
I'll tell you exactly how it came about is I think Sriram Rajamani was Tom Hensinger's PhD student, and Sriram had graduated and gone off to Microsoft, right? And they were working on SLAM.
Mhm.
And I think at some point, maybe 2000, 2001, whenever, somewhere around then, Sriram came and gave a talk at Berkeley. And and Tom, after the talk, we sort of gathered in Tom's office, was like, that's cool, but I think we can do better. Surely there's some better, you can do better. It seems like very wasteful to kind of do all this work all over again. And then we were like, that's a good point. And then, yeah, I think we just sort of sat around trying to I think it sort of just started with this Tom's. It's like, do you really have to like you do all this? So the way, okay, well, let me rewind a little bit, right? So the way, say, SLAM works is roughly speaking, somebody gives you quote unquote an abstraction of the program. So again, the program is now infinite states because you have, a bunch of variables and they can take on, they're not Booleans, so they have a bunch of values. And so the big insight in SLAM or with predicate abstraction was if somebody gives you a set of predicates, so just, logical predicates, you can take a program and you can make it finite state because there's just finitely many combinations of those predicates, right? First one is true, second one is false, etc. So roughly speaking, I mean, I'm being very coarse here, right? Is with SLAM, what you would do is you would say, okay, here are my whatever 100 predicates. You take the program and you would build this sort of finite state abstraction of the program with respect to those 100 predicates, and then you would check it. Now the trouble is, remember it's a graph search problem, and so you might end up, because it's an approximation, you might end up reaching states that you can't really reach just because your abstraction is too coarse. You've lumped too many states together. You need to kind of make the states a little finer. You need to split these large clumps into smaller clumps. And so in SLAM, they would say, okay, now we learn, okay, we need this new predicate. And so we're going to now begin with 101 predicates and start this whole process from scratch, right? And so Tom's point was that seems kind of, not very good to start everything over from scratch because maybe there's a whole bunch of work you did earlier. Again, if you think of it as a search that you're doing, maybe there's large parts of the search that you can be sure, okay, there's nothing bad over there. So we just need to pay our attention and do any finer grain splitting on this side over here, right? So yeah, I think we were just kind of noodling around this particular idea. If you just think of it as a search and you want to reuse parts of the work you've done before, then how would then what would that look like? And I think from that, lazy abstraction is kind of it's basically what you'd get, I think, if you kind of squint at it a little bit. This is roughly my recollection.
Yeah, and then I mean I'm curious. I mean, then you moved on to work on lazy languages, right? At some point, I guess.
Different lazy, yes.
No, yeah, no, but I'm curious about, I mean, maybe philosophically about the notion of lazy, right? Like it seems like it's good to some extent,
Right.
but it seems like it pops up in many different areas. Like one could argue that nature is in itself lazy, like quantum mechanics is lazy, like it doesn't, it doesn't compute until you observe it or something,
Awesome.
and then it's like, okay, now I'll give you what you want. It doesn't
Right.
evolve until someone really needs the answer.
Right.
Then and then we have lazy languages, and we have all kinds of lazy stuff in computer science. Like I wonder if there's something fundamental there. Yeah.
Yeah, I mean, it's just, well, yeah, I guess it's just frugality, as we like to say. It's just, yeah, I mean, it's one of those things where this process of abstraction was so expensive at the time because you had to
Mm.
make, all these theorem proof of calls or whatever that you just want to minimize it. I think, yeah, it did make it. I'm not sure if there's anything super. It's just, I guess it's an optimization that pops up in a bunch of, don't do stuff unless you really have to do it. I mean, it's the way I live my life in many regards. You really need to do this. Voice from above, by which I mean my wife says, yes, have you taken out the trash already? I'm like, okay, fine. Take out the trash. I do tend to gravitate a bit towards that sort of thing. Yeah, I'm not such a fan of the lazy languages, to be honest. I know we wanted it's a shifting topics.
It's a very dangerous topic to
Yeah, I don't like. I'd rather not. The laziness by default is not my cup of tea. Let's be clear. But I like half. Yeah, I just pretend it's not lazy. Um,
Sure.
yeah, it's just like,
So this
yeah,
is tangentially related, but we're talking a little bit about like, the splitting and recombining of these
yep,
various versions. And at least in my abstraction of your career, please tell me if I'm wrong, that the next big step is about type systems. That is about languages with very powerful type systems.
right.
I guess I'm always interested in when people make a change like that. That is like like when you decide not to just keep on doing the same stuff from grad school. Like, was there a particular was there anything that happened that meant you wanted to do something different?
Well, it's first of all, I will say it is to me amusing that Aus is on this because Aus is one of the few people who has pointed out to me that in fact it is the same thing. I didn't
Sure.
actually change. Do you remember this conversation from a long time ago? The liquid types is actually secretly just the same thing. Uh, but the way it happened was, I'll tell you what, I mean, I remember how I alluded to this conversation with Joseph Gogan, right? Where Joseph Gogan's like just kind of thing where you're just doing this brute force thing is uh, is sort of unpleasant. So that was that. But to me, the sort of wall to me, it was actually a very organic development. It was not a big jump. It's one of those things where after the fact, it looks like a big jump just because the papers sort of were written that way. But I ended up there in a very, very kind of gradual. So the problem that we had with, say, with lazy abstraction, and I would say with all of software model checking, I'm going to generalize with all of Floyd-Hore logic. This is my beef with Floyd-Hore logic, is that because to me, Floyd-Hore logic is actually symbolic model checking, as I have said before, right? You're doing this thing where you're really just state, next state, and so on and so forth. Is to make an analogy that I like to use, it's it's a sort of very high precision way to reason about your program, but it's a very slow way to do it if you want to sort of gather information from that's sort of from, that has to travel very far. Let me give you a very concrete example. Let me not wave my hands. Let me give a very concrete example, okay? Imagine you have a, imagine you have a data structure. It could be quite a complicated data structure. It's just a container. So you just have a polymorphic container, okay? It's a box or an array or whatever hash table, right? Now, the trouble with things like with any kind of software model checking or Floyd-Horse style, imagine I have my complicated hash table library, right? Let's say that. I have my client of a hash table library that happens to put in, keys that map, I don't know, it just puts in, let's say, natural number keys. Okay, the keys are natural numbers, and let's say the values are natural numbers that are larger than the key. I don't know, it doesn't really matter. There's some property about the keys and the values, right? That's in this hash table. The trouble with how software model checking sort of propagates information around. So, in line one, I sort of create a hash table. In line two, I put some elements into the hash table. And then in line three, I do a bunch of stuff. And then whatever, in line four, I start pulling out the values from the hash table. Let's just say, right? Now, in the software model checking sort of view of the world, you have this very annoying thing where, well, right up at the top, you created, the key, that the thing that you put inside the box was, let's just say, a natural number. Now, I have to take the fact that that was a natural number and essentially push it through the entire hash table implementation, all the shenanigans that happens inside the hash table, all of that stuff. And then it sort of pops out at the other end when I get the value out, when I do the get, right? Like, oh, there, I got a natural number back, right? Whereas the type system view is like, wait, it's a polymorphic hash table. You can totally short circuit all the crap that happens inside the hash table. It was an A, it was an alpha, right? You put in an alpha, you get out an alpha. And all you have to do is figure out what that alpha was when you put in, and it's the same alpha that you're going to get out, right? So in the type C sort of view of the world, you don't have to think about the hash table at all. You have this very nice kind of compositional view about all of that code, which is just captured by the type signature, right, of the hash table. And so all the liquid type stuff really came about. And by the way, I think of that, to continue my analogy, I think of the types as a kind of mass transit. If you think of this as sort of shoving information around, I think of the type system as, it's really like a kind of mass transit, and the model checking is a kind of last mile, pedestrian or somebody on a bicycle or a scooter, right? Super precise, but kind of slow. Mass transit, you can have sort of these coarse grained blocks of information. Alpha, I don't really know. Was it a nat? Was it an even number? Who knows, right? It's just an alpha, and I don't talk about what the exact alpha is. So anyway, all the liquid type stuff came about because we were sort of constantly getting frustrated with, oh my God, if I have hash tables, I have linked lists, I have to come up with really complicated sort of invariants about these, and it's really hard to come up with invariants about these. And lo and behold, wait, the types people already have these really simple invariants. There's just the type signature. So is there some way to kind of mash these things together? Um, so yeah, it sort of took a while, but ultimately that's what's going on. And in the back end of all the liquid type stuff is actually model checking. It's really, I mean, the way it all works out is you have the type system sort of, doing this mass transity thing. There's a system of constraints, but then at a low level, the individual constraints are actually classic, just model checking constraints. And the somewhat surprising thing to me is, I did all this stuff with lazy abstraction. Um, but right now in our own sort of liquid types things, we just have this really dumb solver, which does very, I would say, sort of 20th century predicate abstraction. It doesn't even do all the fancy lazy abstraction stuff. But the modern Horn solvers actually use the lazy abstractions. They do all this lazy, they do a lot of this kind of lazy constraint solving. So they're using a lot of that sort of technology from Blast in order to solve these quote unquote horn constraints. But yeah, so it was really a fusion of these things. Sorry,
Alex,
I
you were
was
muted.
yeah.
Sorry. I wonder, like, I mean, you were the one to bring the ideas from SMT solving, software model checking to the languages, right? Like, do you think you were like uniquely positioned at a point in time to do that? Like the technology was ripe for transfer or for combination, or like why didn't the languages people, for example, not study much more expressive type systems? I
But
mean,
they
they
did,
have,
by the
of
way.
course, they have, of course, but more with the automation that liquid types.
I would say one of the very influential pieces of work that that sort of feeds into all of these liquid types and so on is the line of work um, by Hongwei Ji and Frank Fenning in the late 90s.
Hmm.
So Hongwei Ji was Frank Fenning's student at Carnegie Mellon, and so they have this system called dependent ML, which was kind of it was I guess there was while George was at Carnegie Mellon, he was doing all this BCC stuff, and so I think the way I hear at least George tell it is that George went and did an internship with Greg Nelson, and he's like, whoa, this stuff is cool. Why aren't more people using they weren't called SMT solvers then, but they were whatever theorem provers. And then I guess Hongwei and Frank were this is basically all in the late 90s. So there was this stuff. Um, I think I suspect it's just a cultural thing. It's yeah, it's as you said, I was just kind of exposed to this more. I saw this, as I said, in my very first semester in grad school, we built an SMT solver again, built a theorem prover. That was the class project. So I was just sort of in my head, and I was using this technology a lot, and I just wanted to um see more of it. That's my sense. I suspect that in the PL world, where they of course have very fancy type systems, sort of classic dependent types, they've been the way I like to think of it is the underlying machinery is sort of based on unification. This is the core. There's a lot of really sophisticated dependent type theories and so on, but they're all based on unification as the core machinery, instead of these kinds of instead of SMT style decision procedures. So I think, yeah, that was, I guess I was really just bringing that. And then this business of doing this sort of fixed point, this model checking kind of view, to, doing this kind of inference, as it were. Because without that, it's somewhat painful, in my opinion. So yeah, I think I happen to be, sitting at the right kind of vantage points.
Yeah, yeah. And speaking of those like this like kind of powerful programming languages, powerful type systems. I mean, it seems
Mhm.
like now there's like a renaissance of strong type systems. Like maybe Rust is a pioneer there, at least the mainstream. But there's a lot of interest in things like I don't know, like Lean, for example, a wide interest, right? So
Right.
what do you like? What happened there? Like why now? Like what's going on?
I I mean, the lean thing is quite remarkable. I mean, if I alt tabbed, I have a lean window open somewhere myself. The lean thing is quite remarkable because yeah, it's really exploded. It's quite fantastic. I mean, yeah, I don't have any theories. I mean, with Rust, I also find very interesting because um, let's see, what is my theory? I guess my theory is, again, if you go back to the 2000s-ish, there was this kind of view that sure. So there was Java and C Sharp, right? Late. So I remember people saying, "Oh my God, when like Greg Morissette told me this once. There's like when he was in grad school when Java came out, and people were like, "Oh my God," they were really disheartened when Java came out because they were like, "What else is there left to do in programming languages?" Because all this stuff we've been thinking about. I don't know if you ever heard the story from Greg, Adrian. It's like what? Uh, and so there was Java and C Sharp, and then there was this kind of backlash against Java and C Sharp, right? With Python and Ruby and these kind of uh, dynamically typed or uni-typed or whatever languages, and people are like, oh, static typing is dead. Everyone's all Java and JavaScript and whatnot. And then there was all this research on trying to sort of retrofit gradual typing and what have you. And now over the 2010s and so essentially all the JavaScripts and what have yous have all sort of sprouted a type system of one form or the other, right? Like Python has like 12. Uh, so I think what happened is programs got bigger, and so people just started to see. I mean, and to me now the whole static dynamic ship has long sailed. That's it's just like the debate is over. So I mean, with Rust, I find fascinating because it has a very complicated type system. Let's just be very clear about this. In my opinion, Haskell has nothing on Rust. Okay. It's just, I mean, it's a breeze programming in Haskell. I didn't have to like go to my grad students when I got a type error in Haskell. I could fix them myself. With Rust, every so often I have to get on the horn with my student Nico. Nico, I have no idea what's happening here. Please help me. That said, what Rust has, despite its great complexity, is that they have just ridiculously good error messages, to the point where you can just, I really don't know what the thing is, but Rusty tells me I should put a star over there. I'm just going to put a star there. I don't know what's happening. It says put an and there, go put an and there. Just like, you just keep doing the boop, 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 and everything is great. It's like, okay, well, sweet, we're done, right? So the error messages are just so good that I think people are willing to. And the other thing, of course, that people, I think forget is of course, the error messages are really good and the tooling is just fantastic. But B, there's a kind of very compelling value proposition, right? You do the types and you don't have garbage collection and your code runs really fast. So it's like, it's harder to sell sort of types or so on correctness as this kind of nebulous. There's this very nice set of slides that's doing the rounds in case you haven't seen it. Mike Dodds, N Things I Learned Working, doing formal methods in industry. Mike Dodds is a researcher at Galois now. So he has this nice set of slides on, his job is to kind of sell formal methods. And one of his things is like people need to see you can't, one of the, he has this nice graph where he says, you can't have your curve look like, oh, this is going to come out the right way. You can't have it go like flat, 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 6 months, nothing, and then, oh, look, massive wins after 6 months. No, you have to give people a kind of gradual wins all along the way, right? So I think Rust really gives you that in space. You sort of get a performance boost on. Lean is a mystery, I mean, I will say this about Lean. It is, again, really, the tooling is so slick. You have no idea how easy it is to install Lean. I don't know if you've tried. It's ridiculous. You
Yeah.
literally open up VS Code and you create a file called bob.lean and it's like, and it's like, what? So it's really quite something. And yeah, they've built up, I mean, for example, I have a friend who, who has a son who's in high school, and the son is going to, it's just like, he goes to high school in Oregon and he's going to go to a math camp. And he says, look, this is what they're doing in the math camp. I was like, oh, let me see. And he's like, oh, no, no, week one, whatever groups, this, that complicated thing. And then week 12, formalized mathematics in Glean. I fell off my chair. This is just like, wow. So
Graduation.
really, um, it's very impressive. Yeah.
You don't leave the
Wow.
camp until your proofs go through.
Yeah. Just 1 week. And it's hard, I mean, I'm trying, it's not easy. It's just, yeah. Um, yeah, I don't know
Yeah,
what.
I think it's like fun to contemplate. Like, obviously, there's like a long tradition of the pendulum
Right,
broadly about types swinging back and forth, if you know what I
exactly.
mean.
Right,
I just
right,
think it's interesting, like that like the specific way it manifested this time is in
right.
like several different ways. Like you said, there's like the TypeScripts of the world, but then there's also the value proposition, like the thing that you get from the hard types with Rust, and then at the very end of the
Exactly.
spectrum, now we have Lean, which like it's not clear, but like, is it just correlated? Is it all happening at the same time for no reason, or is it like
Right.
is it all part of something sociological? I don't
That's
know.
right. Well, I think people have realized that, I mean, there's also probably a bit of a network effect, where
Sure.
people realize that there's a lot of sort of knock-on benefits you get with, just like APIs and just sort of more better documentation and so on and so forth. So, yeah, I think that's my sense.
So speaking about Rust a tiny bit, I know one of the things you've done recently is explore refinement types in the context of Rust. Could you tell us
Yeah.
about that effort and what it's like? And if you want to, now is when we prep you that you might want to
Oh,
do a demo if you feel like it.
oh, sure. I would be very happy to do a demo. I mean, well, yeah, so I mean, let's see. I mean, well, I don't know how to, what sort of, I should have some sort of can set up for the demo, right? I mean, the high level bit with, I guess, refinement types, liquid types, and all this stuff is I wanted to get to this point where the programmer is the person who's sort of guiding the tool. I mean, to me, I've sort of given this talk a bunch of times where one of the things that I don't like about, or it's not so much I don't like, I think we need to get beyond, is where you have some set of people who are writing the code, and then you have some people who are somehow analyzing the code and are going to tell you, oh, why don't you fix these 7 things? In my opinion, this should really be sort of happening. It should be the same person, and they should be kind of fixing things as they go, right? So, I mean, what I like about sort of refinement types or liquid types is that, I mean, the hope is it just gets jammed into programming. And so I think that Matthias Felison sort of puts this nicely. You want the kinds of the ways in which you're writing your specs to sort of dovetail nicely with, how you think about the code. It's the same as this analogy I made with the hash table, right? I don't think about sort of pushing this individual invariant through. I just say there was a hash table of alphas and I popped in an alpha, which was a nat, and I get that nat out. So anyway, maybe I should just do a demo. Can I share my screen and so on? How does that work?
Yeah. Yeah.
Let's hope nothing blows up. Aha. There's always a chance of that. Share. Let's see if I can find wrong window, blah, blah, blah. Here we go. Okay, cool. So I'll just show you what this feels like, right? So share. Can you all see this?
Yep.
Yes.
Participants can now see your screen. I can hardly see it because of all the Zoom jim jams. Okay, cool. So let me just, so this is some Rust code. And so I mean, just as a brief bit of history, I mean, for the longest time, sort of I was looking at this type system thing, the sort of refinement liquid types in a purely functional setting. So we started with ML and Haskell and so on. But I ultimately wanted to make it work also in imperative language. The trouble with imperative languages is, well, they're imperative. But the really cool thing about Rust is that once you've gotten your code to sort of type check with, the borrow checker and this, that, and the other, you can start, it sort of starts to feel very functional. I mean, I don't want to get super technical about it, but it gives you this very functional sort of way to reason about your program. So let's just jump right in. Okay, so there's a bunch of Rust code, but it's not using any fancy Rust features, right? So I'm writing a function called assert. You can see this. Is the font too small? I'll just blow it up a little bit, right?
Looks great.
It looks great, right? So here now, what I want to do is I want to say I want to make this function be a test function. So I want to say that this function should only be called with true, okay? Because otherwise, whatever, something bad happens at runtime, right? So it's like an assertion. So with the system that we've been building called Flux, this is what you do. You write, if I get this, oh, why did I not let the autocomplete? Yes, thank you. So this looks just like the Rust signature, right? It says I'm a function that takes as input a Boolean. But now here's the key bit, is I say that you can index. So this little thing over there is what we call an index. And it says that this Boolean must always be true. It must be the Boolean true, right? Otherwise, I will yell at you. So now when I hit save, oh God, no bugs detected. Why? Oh, right. I remember why. Because I disabled the demo. Let me not ignore this. I'm going to comment that line out to see a bunch of errors. Okay. So now you'll see the ID sort of starts yelling at you. It says, well, this assert 10 minus 2, that seems, dubious. This condition cannot be proved. So the SMT solver sort of kicks in. And of course, if I fix this and I make this 10 less than 20, then it'll work out, right? Let's look at this one. So I've defined a function called inc. Inc takes an I32, returns an I32, and it's entirely modular. So the only thing that the type checker knows about inc is its type signature. It takes an I32, it returns an I32, which is a 32-bit integer, right? And so I don't know that this 10, which you and I can see, well, this is 9, so 10 should be 10, right? And so here what I want to do is to write a little signature that says something like, okay, well, and so here what I'm going to say is that it takes as input some integer x, and it returns as output the I32 that is x plus 1. Damn it. There we go. And so now that sort of goes away, right? So this is just the sort of the most basic thing. So let's kind of go a little further. So here I say, here's a floating point division. It takes a floating point number and it takes some weight, which is just a U size. And I'm doing a division, so I put a little assertion here, and this assertion is failing because y is not in fact, there's nothing here to tell me that y is going to be greater than 0, right? So why should that? So now one sort of nice thing you can do is you can sort of following this thing where, you sort of want to follow the programmer's, abstractions. What you can do is something like this. You can say, well, as far as um, weight is concerned, it's not just any old U size. It is, in fact, it is a special thing where it is a U size, which is values, all of which are strictly greater than 0. So now so wherever I had weight written, the flux, which is the refinement type checker, is going to make sure that they are strictly greater than 0. And so now what's happened is you see there's a whole bunch of problems further downstream where I was creating weights where it would yell. So for example, let's just say if I now did something like, I don't know, fn foo, and I say foo returns a weight, and I return, let's just say 0, then with any luck, I would get an error, right? Because of course 0 is not, right? Because of that particular error. So I'll remove this. Okay, great. So let's move on. So here what's happening? I was hoping to see a whole bunch more errors, but let's see this. So okay, let's look at this. So you can start doing more interesting things. So for example, let's say your how can I get like 2 more minutes, 3 more minutes?
Yeah, take your time.
Okay.
Go for it.
So let's look at this little function. So this function is supposed to, it sort of takes as input a vector of F32s, right? Floats. And it's just it's a straightforward imperative loop that wants to just find the element in the vector whose value is the smallest, right? So is it the 6th or the 9th or the 12th, right? And so now what's happening is this A of I and A of min. So what do I do? Min is initially 0, right? The minimum index. And then I loop over the range from 0 through A dot len. And I check, is the current index A of I less than my known index minimum? If so, I update min to I. And then at the end, I return min, right? This is as straightforward. There's nothing fancy going on over here. But the type checker is unhappy because it's like, well, I can't prove this precondition. So what is the precondition here? Is what I've done is I've taken this vector library, okay, and I have refined it. So I say something like the vectors have now sort of carry length information, right? And what's happened is that the get method for vectors now says that it takes as input the vector, which is of whatever is of some size n, and it must be given an index that has to be strictly less than n, right? So that's the precondition that you can sort of specify. And once you do that, now it's like, well, I don't know that these are within range. Okay, because how do I know this I is some random number? How do I know it has anything to do, right? And so what we need to do is we want to go back and say, well, and I is taken from this range of 0 through a dot length. And so this range function takes a low and a high, and it returns a vector of indices, right? And now this is one of those things where, well, there's something interesting about those indices. So I want to say that it's a sig. And now let's see, no, come on. Don't make me type it out. That's no good. FN. Oh, sigh.
Is
Okay,
this
fine.
Copilot or that's
This is Copilot. Yeah,
okay?
this.
So
Okay.
somehow it knows about flux, I guess. It's a seen enough.
It's,
We
I
can
guess,
forgive it for not being perfect.
So let's see, actually, let's see what it's, I mean, it's probably seen my other code windows or whatever, right? So now what we're saying is that it returns as output, blah, blah, let's never mind the size. Okay, so we could talk about the size of this guy, but really all I care about for now is that this value is a value that is between low, sorry, right? It's a value that is greater than, oops, right? And the value is less than high, I think, if I recall, right? Let's see, is this
That's right.
happy? It's like, yeah, this is happy. And in fact, what I had said was that the length of this array is high minus low. Okay. Um, and this, let's see, if I hit save, you'll see a little squiggle over here. Let's see what the squiggle says. Refinement type error view problem cannot be. Let's see, what is precondition? This is the condition that cannot be proved. What is the condition? Oh, the high minus low bit. And the reason it can't be proved is because actually it's not true. High and low could be like, low could be 10 and high could be 5, in which case I'm claiming I created an array of negative size. So it's only true if there's something about this high, which is that low is, I think, strictly less than high, something like that. Okay. And so now at this point, I'm saying I'm give you a vector of elements, all of which are between low and high. And now notice there's no sort of complicated logical formula here. It's just as I'm just talking about a container, and every element of the container satisfies this property. Oh,
So
look.
here
Yeah.
V is like a placeholder for the return type. Like you could call it anything. It's an
No,
existing
it's a, see, look,
type.
look at it. It's kind of like, so let's just parse this bit over
Yeah.
here if I can. Let's just, okay. So what it says, it's a U size, and
Mhm.
each V represents an arbitrary value of that U size. So it's a U size where each value is called V, such
Mhm.
that that V is between whatever low and high, right? Much like what we did over here. Weight is U size of V's. You can think of it as this, if you
Mhm.
like, right? This
Yep.
such that, I mean, I could literally call it this, I think, this, where this is greater than 0, right? Or, and so on, right? And so now over here, so that look, that I and that error went away because now I know that I is always between 0 and a dot length, right? And a dot length returns the length of a. But this min is still yelling, and this is an interesting one. I wonder if you can figure it out. Do you know why it's complaining? This is, I mean, this is one of the slightly frustrating things. I wish it would, like, if this was Rusty, it would tell you exactly how to fix this problem. Replace min with like something. Can you
Well,
guess what
if you
my...
want a low quality guess here, there's just trouble with the fact that it's with mutation, that is like Rust doesn't want to infer anything from, like, because you're sitting on top of Rust, it just guesses that this is a usize and not a refined type.
No, it's not quite that, because I mean, unfortunately, I wish I wish our error messages were better, but in fact it does. So, but I'll give you a clue, which is, suppose I replace this min with 0. Wait, why did that work? Oh, interesting. Okay, there's a subtle reason why that works. But
I
let
think
me not go into that. The trouble here is that the array might not be empty. I mean, the array might be empty, right? So that's the real reason over here is that min is any number that's greater than or equal to 0, and it may not be safe to index the array at that particular position. And so what I really want to do over here is I want to say, don't worry, I will call you only with an array that is in fact not empty. So let's see if flux sig, no, there's no n over here. I'm going to say the size is some k, but okay, fine, n was fine. There was nothing wrong with n. But this n is oops, sorry, greater than, it's a non-empty array, right? So you can't compute the minimum of an empty array, because then it's not going to work out so well, right?
Here, the at n just refers to the size, like by convention, like when you put it in.
Exactly. So what this is saying is, so remember in the earlier, so if I go back up over here, so let's just
Mhm.
pick this U size. Okay. So why did I not? So here low, I had a parameter name for the low. It was literally a parameter, so I could just use it, right? In this case, the actual parameter A is a reference to the vector. So I can't really talk about, the reference itself doesn't have a size. And so we have this way where you can say, okay, it's a reference to a vector whose length is n. And so this n is essentially, it's a binder that gives me the length of that vector, if you wish, right?
Mhm.
So that's what's going on. So that's an excellent point. So anyway, I can sort of go on and on. Well, let's do this one last one, right? So compute the Euclidean distance between 2 points x and y. So here what I've done is I've taken a vector of f32s, and I'm going to call it a point. I'm just defining a type alias for it, right? So I don't have to type quite so much. But now I'm defining a refined version of the point, which takes a parameter n, which says how long, what the dimensionality of that point is, right? And so now I'm getting an error here because I'm sort of, let's look at this. It's just Euclidean distance, right? So I'm going from 0 through x dot len, and I'm doing xi minus yi, and I'm squaring, and I'm adding the results up. But this might be out of bounds because I don't know that y and x have the same length. And so you sort of keep going, and you might say something like flux, colon, sig. Okay, fine, you finish it. There we go. Okay, so not bad, but I have to tell it which one is the parameter. So I'm going to say the at end, and now that thing goes away, right? So anyway, there's a whole thing. If we had more time, I could, it sort of works out quite nicely because, there's a whole, long story short, it works out. There's this kind of k-means, and it uses a kind of map and a reduce operation, right? Which I alluded to these hash tables earlier, where there's a whole bunch of complexity in the implementation of the map and the reduce. But the only thing that the type checker knows over here is the polymorphic type of map. It literally just knows that map takes a vector of t's, a function from t to u, and returns a vector of u's, and that vector has the same length, right? And the same with reduce. So it just uses the type signature and is able to sort of plug in the right things for the k's and the v's and so on and so forth in a way that kind of lets you verify all of this. So let me just say that and not take up too much more.
It's pretty sweet. So the way it works, I'm guessing you first run the standard Rust type and borrow checker,
Correct.
and then from there you take the types and then you do kind of liquid type style reasoning with SMT solvers in the back end, right?
Exactly so. That's exactly
Does
right.
the borrow checker help you at all, like in simplifying the constraints, or I'm just kind of guessing? Like, is there
It
something? Yeah.
it helps us in that in a very unobtrusive way. It helps us a lot. So the reason this all sort of feels very nice is because, so let me put it to you like this. So for example, over here, when I say something is a point n,
Mhm.
um, implicitly I'm Rust. So the Rust type signature over here says that the length of this y does not change. It's
Mhm.
not immutable, right? So essentially what the borrow checker is giving us is precise aliasing information. So it tells me, look, it was a whatever read-only borrow, right? And so any invariants I know about it just do not change. It's giving you, think of it as, if I may get a bit technical, it's kind of giving you a bunch of free separation logic style framing rules. And you just get it for free because you don't have to like push this around and you don't have to track any information. So we entirely just rely on the borrow checker for that. If you say that this function takes as input an and whatever, an and point, then any invariants that held at the call side on the point just continue to hold afterwards. And this is precisely where this kind of functional feel comes from. Because most of the time you have and points. Sometimes, of course, you do have and mutes, in which case there is a way. So for example, let's just go back if I might. Suppose I change this ink, right? And I make this, one should never do this kind of thing, but here we go. Suppose I make this an and mute, right? And I'm going to not do this, and I'm going to return, how does one do this? Gosh, I think it's star x is equal to star x, whoops, sorry, plus one, right? So this is now a super
That's right.
imperative thing, right? Now here what I would do is something like, whoops, sorry, oh boy, star x. So here what I would do is something like this would become and, so you can, there's sort of multiple things you might write, but here I'm going to say it's an and strong to an I32. And what this means is that I can say something like ensures that after we're done, so the starting value of this I32 is, let's just say n. When I am done, x will point to n plus 1. Okay, so this is how I'm getting what types people call sort of strong updates. So it's the same location, but it gets updated. And so now here, maybe I would change this to, oh God, help me. This would be an and mute, right? And this would be a let mute. Because now Rust is yelling at me. And now this 10, no, there's no 10 over here, right? So here, maybe this
Assert 9 equals 10 is a great assertion to have written in your code.
I wonder if this. Oh, it worked. Yes. Hallelujah. Yes. So it works out quite nicely. But again, all of this is because Rust says it's an and mute. So we're like, okay, then you want to do sort of strong update shenanigans. But that's the extent to which we use the borrow checker. We don't actually know anything about lifetimes and so on and so forth.
Right, it seems like I'm imagining like a different version of this where Rust was unconstrained. You can imagine that the job would fall to Flux of having a whole bunch of aliasing contracts on all of the parameters, saying that like this doesn't alias with that, or like I promise not to update this or something, but that you kind of obtain from the Rust type system.
Exactly. And I mean, I've been sort of working on trying to get an imperative refinement type thing for many years. There's like, I mean, back in 2010, we wrote one for C and then one for JavaScript and one for TypeScript. And the trouble with all of them was like 80% of the work was exactly what you're saying, Adrian, right? You had to first build in this layer of non-aliasing, and that just got really annoying. But it's with Rust, it is, you get this for free, by which I mean it's like Simon Peyton-Jones has this thing where he says, when somebody says something is for free, it just means you've already paid for it. And so that's what's happening with the Rust type checker. It's like you're getting all this for free, you already paid for it just by getting your program to type check, under the borrow checker. So once you have that, you get all this kind of non-aliasing information, just, so all this work that we had to do with this earlier C stuff where we're tracking non-aliasing, this alias to that, like we don't have to do it because the Rust people just do it, take care of it. So yeah, it feels quite nice. It just, yeah, it feels very ergonomic to use.
So speaking of Simon Peyton-Jones, you two and a number of others released Verse, which is a new programming language. Maybe tell us about it. What's the philosophy there? Yeah.
What is the philosophy of Verse? You mean the programming
language?
Yeah.
Yeah. Like, I mean, it seems it combines functional and logic, which is
it's
very far paradigms, I guess.
An interesting language. I think, I mean, there's, yeah, I think the idea with Verse is we're trying to, so I mean, I like functional programming, of course, and but so first of all, let me rewind. So Verse is like mostly the brainchild of Tim Sweeney, who is the CEO of Epic Games. So Tim has been sort of thinking about Verse for decades, like literally decades. He's been thinking about it for maybe, close to 20 years. And so when I started there, I started working with Simon and Leonard and Kuhn, and now Jan Vitek is there. It's just a bunch of really terrific people. We are sort of trying to take, Tim's vision of, that. So Tim has this vision of what. Whoa, something just happened.
I just stopped the sharing.
Oh, good. Okay.
Good point.
has this vision of, so I guess Tim likes functional languages, but he also wants all this stuff with logic programming, because in the games world, they have a bunch of things like, well, I mean, the kinds of problems that show up even just in classic OO, where you have a bunch of objects where A depends on B, B depends on C, C depends on whatever, D, and then D depends all the way back on A. So there's like you have this chain of four different objects, each of which are pointers to each other. And the way you would sort of initialize them in C or Java is you start off by, making those pointers null, 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 and then you do some shenanigans where you kind of, one by one go and set those pointers, right? So Tim has this view that, well, you shouldn't have to do that. You should just be able to write a bunch of equations that describe the relationship between these four objects. And then you should, the language runtime should be able to just solve that thing out and, fill in those slots. And that's a kind of more bulletproof way of getting this kind of thing right? So that I would say is sort of one part of the philosophy. And the second more radical part is actually verse has, but this we haven't, nothing has been published, but this is what we've been sort of banging our heads on for, well, the last year and more, is that it has a very sophisticated type system. And the type system is actually one of these things where the types are actually just verse code. So you can just like pretty much write, it's kind of like scheme contracts, but in this kind of logic programming sort of style, and they're supposed to be sort of statically checked. And again, there, Tim's vision, it's quite remarkable, is that the idea is that this is going to be sort of programming the multiverse, no, the metaverse. What do they call it? I should know this, right? The metaverse, I think, is
Some kind of a verse, anyway.
some sort of verse, right? As the name suggests. And he really believes in sort of having contracts that, so that, if Adrian writes, some sort of mod and Aus writes some mod, then these just all get published. And then, the compatibility of these mods, you can't have Adrian's mod sort of blowing up the whole of Fortnite or blowing up the whole metaverse, right? So he wants a lot of verification. So anyway, that's why there's this very sophisticated type system. So
That's
yeah,
pretty cool.
that's the vision, but it's also just it's a very interesting language. And yeah, it's a very interesting language. There's lots of little interesting features that interact with each other in fun ways.
This is maybe an ignorant question because I just don't know that much about verse, but does the contract checking, does it look refinement typey at all? That is like, does it use an SMT solver, or is it something different from this?
It's well, I mean, right now, as I said, it's still very researchy. So it looks refinement typey, as in the contracts, they sort of look refinement typey. Um, but it's not, it almost, and I mean, the question, does it use SMT solver, is one that is sort of actively being debated, because at some point we'll want a decision procedure, but it's not clear whether we want like a full-blown SMT solver, or, I mean, right now the closest thing, whatever our little prototype sort of core calculus implementation, we just like, okay, it's not an SMT solver, but here's a little decision procedure for arithmetic. Let's just pulled in, and okay, we have a little congruence closure, and it's starting to look a lot like an SMT solver, but it doesn't at all look, I mean, the way that it works is not at all like refinement types. I mean, it's a bit, it's a bit hard to, it's perhaps the closest thing is to Sam Tobin Hochstadt and Dave Van Horn and their student, I think David Nguyen, work on sort of static contract checking for scheme. It's kind of closer to that in, how the mechanics of things work than to refinement types as such. But yeah, it's very much, someday we will write a paper, hopefully soon.
So maybe we can, going back to your demo, and
Yeah.
maybe taking a tangent from there. I mean, you were helped by Copilot, right? As you were
Yeah.
writing the dependent types, and of course, now LLMs are like all the rage.
Mhm.
Like, I wonder, what do you like? Where are things going in your view? Like, is it gonna make people program in these more, powerful languages because it just makes it easier to write complex types and verify them? Or alternatively, it could also stifle programming language design because it's highly dependent on having a good corpus of training data. Like, if you design a new language, and and you start coding in it, like Copilot probably won't help you as much.
I lean towards the former, to be quite
Okay.
honest, because I'll tell you why. So to me, one of the one of the big sort of stumbling blocks with these sort of fancy type systems. As you saw, I was like, I mean, I myself, when I wrote the tool, I'd forgotten the syntax. It's like, oh, which one is it? Curly brace, whatever, right?
Yeah.
And what I have found is that it's like, when we write a paper, you have your student or whatever write the first draft, and then you can correct it. And you can, significantly correct it or improve it. But writing the first draft is often really, really hard. And so so the Copilot thing almost gives you, here's the first draft. It's like, I think you're trying to do something like this. And it might be totally wrong, but it's much easier to go and edit what Copilot gets wrong, in my experience, than to write something with a blank slate, right?
Mm.
And so that is one. Two is, so there's a bunch of people who've been sort of trying out sort of Copilot and Copilot-like things, and it's surprising they work. They work quite well. So I have well, I guess it's after the review. Anyway, I wrote this paper recently where we took a bunch of liquid Haskell things, and this was not individual functions. We just took the whole. It was like a library with, I don't know, like 150 functions or something, right? And we just wanted to say, okay, fill in all the type signatures. So here you saw how I was going through one, and each type signature depends on the next one, right? So we're like, just do this thing. I guess the AI-ish word is, you wanted to say you wrote an agent that goes in and like writes the signatures and then does some backtracking search. Oh, not that one, guess the next one, right? And and again, so this was liquid Haskell. So it's not like there's a lot of liquid, a Haskell code, and certainly not liquid Haskell code, right? But we took libraries that were not. So we used, I think it's called Star Coder, which is one of these open source LLMs where you know exactly what it's trained on, right? And we made sure to pick libraries that were not in Star Coder's training set. And we found it does really well. It actually, and so it's not going to get the whole library. It's going to query you it's like, okay, I'm stuck over here. I need help, right? So basically, imagine it's doing a kind of search through the call graph, right? Trying to guess types, and as it guesses, then goes to the next one, goes to the next one, it might backtrack, etc. And basically, don't quote me, there's not exact figures, but roughly speaking, 80% of the function signatures it can kind of just guess. And so 20% of the time is going to be like, hey, I need some help over here, right? Which to me is pretty good. So I'm optimistic. Maybe I'm just naturally I'm lazy and I'm an optimist. So I'm optimistic that it'll make this kind of thing much easier, because like I mean, just to pick a completely different example with um I want to teach this. I'm going to teach a formal semantics class in the winter, and I wanted to use Lean. So I've been sort of, and so first I started off. So I wanted to use this very, very nice book called Concrete Semantics by the Isabel people, Tobias Nipkow and friends. So, and I want to focus more on the types and the program analysis and the semantics, and not so much on the mechanics of the theorem prover itself, right? And so I was going to start doing the stuff in Lean. And chapter one, it would just like forget the proof. It would guess the theorem too. It's like, okay, the next theorem you want to write down is this one. And then like, and so I was like, oh my God, this is terrible, because how am I going to teach this class? But once I got to chapter two, it was all rubbish, right? So all the predictions, once you get beyond the really hello worldy examples, the predictions are rubbish. But every so often, it's, I think, what the HCI people call discoverability, where I don't know what the tactics are. And the weird thing to me is Lean, the, the documentation for it for computer scientists is not, there's no software foundations for it, let's just say, right? So in fact, there's not such a nice learning curve, in my opinion. It's quite steep. So I'm like, well, friends, what am I supposed to do here? And Copilot often, is like, well, have you, like, it's just belching out some tactic, which is quite useful. Which is then I go and look for it, like, oh, what does this thing do, right? Um, so often it's completely wrong. And in fact, 90% of the time it's completely wrong. But that 10% of the time, it says pretty helpful things that I can just, as a, hey, think about blah, right? And so I would say it's been quite good. It's been sort of entirely positive. It's not doing my proofs for me. I still have to do the bulk of the hard work, but it's a really good search engine.
Yeah, yeah. I mean, I mean, in your demo, it was pretty impressive how, even though Flux is, I don't know, a year old and a research
Yeah,
project, it was just like, yeah, I know this stuff. Here's a
it's
signature.
I mean, and sometimes yeah, there was a larger code base I was once working through. There was some bit vector shenanigans, bit vectors and powers of two.
Right.
But the function names were somewhat, and there was a family of them, right? And
Mm.
so the first two, it figured out, oh, he seems to be writing, there's a one and then a two and then a four. And then the next function, it like put in eight and then it put in 16, and then it put in 32. And they were the right ones. So it was quite helpful. Yeah. So I'm somewhere in the middle. I'm not one of these who's going to like, we're not going to have programming to do. We're going to have a lot of programming to do. I'm very much an optimist where it's just going to make it much easier to use these kinds of tools. And it's going to open the door to many of them. Because
My
again, there's very little flux code out there, right? It's just, yeah. Uh,
my favorite experience with having assistants turn on is when they do like a sorcerer's apprentice thing. Like in your example, if it just like keeps going and it's like the next one is like 2024, 2048. How many of these do you want? I'll just keep doing it until
right. Exactly. Yeah.
I find that adorable.
Right.
Yeah.
But sometimes I do switch it off because it's like, okay, this is just don't bug me.
Right.
And sometimes it just gets in the way because like, no, the thing over there is hurting my own thinking. So just like switch it off. Yeah.
Right. So we have a very philosophical question prepared
Ooh.
for you, which I'm very curious to hear. If you want
Yeah.
to reject this question entirely, it's completely okay. But
Yeah.
like sometimes I don't know, like I feel a little bit of jealousy of the theoretical computer science people because they have grand mysteries that everyone can point to and say like that this is something we can all agree is a gigantic like a gigantic ponderous mystery that we all can like can agree is fun to think about or something.
Grand
Like
challenge.
exactly right. So like
Right.
maybe the challenge is P versus NP or something,
Right.
but I feel like
Right.
they're lousy with them. They have all kinds of these things.
Right.
Do you have any sense that we have those in programming languages? Like, do they exist? Should they exist? Maybe we don't need them. Maybe it's like just not part of the structure of what makes PL.
Oh, this was the question that made me intimidated when I saw it. Let's see, I I don't think we, I don't, I, here, I'm going to give an answer. It might sound facetious, and I should have thought about this some more. I knew there was something I should have prepped. I'm going to give an answer. It sounds facetious, but I don't think it is. Because it's like, I remember once we had a faculty candidate. It's a well-known person. She's really nice. And she's like, so what are the big open problems in programming languages? She asked me this. It was Virginia Vasilevska, I'll just say. I remember people was like, I like her very much. So we were just having a chat. They said, Virginia, the big difference within PL and theory is we have no big open problems. The whole thing in programming languages is to find the interesting problems. You don't have these kind of, because in a sense, I just, yeah, our job is like finding sort of carving something out into a technical problem is like 90% of the work. You know what I mean? I guess it goes back to say this anecdote I had about lazy abstraction where Tom is like, well, this seems like a lot of work is being done. Can't you just do less work? And it starts with this very nebulous thing, but that's where we sort of start with that and you turn that into a problem. So I don't, to me, there is a fundamental, if I go to like a cocktail party or whatever, and people ask me, what is programming languages about? What do you guys think about? My semi-facetious answer, which I've sort of put in talks now, is also, well, it's like we're doing what George Orwell, we're trying to do what George Orwell wanted in 1984, right? We're trying to make it hard for you to write bad programs. This is just make it hard for you to think difficult thoughts. So this to me is the fundamental problem of programming languages, right? How do you kind of linguistically, syntactically distinguish bad from good in a way that lets you write all the things that you want to write and not write any of the stuff you don't want to write. Now, what you want and what you don't want is going to, depend wildly depending on the domain or the circumstance, right? But that's the fun thing. That's the amazing thing about programming languages. This is like the central challenge. Now, if you are designing hardware, what you want and don't want is very different than, I don't know, if you're at Amazon designing a language for billing contracts. But at the end, there's always this what you want and what you don't want, and we are somehow trying to coax this or capture this via syntax, right? And it's a very fuzzy problem. It's not as crisp as P versus NP, but I think it's like a family of interesting problems, right? And then, yeah, you can sort of come at it in two ways. You can come at it from the design way, where we're just going to, by construction, make it impossible for you to do the bad things. Or you sort of take the analysis point of view, where well, somebody's written this, and I just want to check if you did the right thing, right? I'm going to analyze it and see if you kind of got it right. But yeah, that's the closest I get to any. Um, I don't. Yeah, I guess I don't worry about it too much because there's another kind of. I just Yeah, it's like I think what you would want it for, like why would you want? I'm just trying to debug. Like you feel jealous because it's kind of a motivating thing, right? To have
Right, yeah. It's like people are attracted to the field. It's like, oh,
right.
I want to, discover this big thing about the universe or about like the nature of mathematics or the nature of computation. I mean, for me, when I was a graduate student
Yeah.
working automated verification, for me it was like, oh, there's this thing that's undecidable, it's impossible, and we want to get there. It's kind of like I want to get close to the speed of light. I know I can't get there, but I want
Right.
as close as possible. So that was kind of a motivating. But
Correct. Yeah, exactly. I mean, we know. I mean, the theory tells you it's not doable.
right.
And yet we are flying in the face of or as I get to quote Sriram Raja when he likes to put it nice, he says, uh, just because something is undecidable doesn't mean that it ceases to become important, or it's unimportant, right? You still have to. So yeah, I think from a motivation point of view, for me at least. I just liked, and I think this goes back again. I think the people who tend to be interested in programming languages are um, people who really like this, like the symbolic nature of the work, right? Just sort of revel in like look at the symbols and the fact that these pieces all fell into place just so it's like, oh, that's so cool. Um, but I guess it would be nice to have grand challenges to motivate sort of external or for funding or things like that, right?
Right.
So that I can get behind. But I'm not so bothered. Like I'll give you like one of the biggest results in programming languages over the last 10 years, I would say 2013, is in one of the coolest projects. I don't know what biggest result, but definitely is the halide work, which I'm sure you are very familiar with, Adrian. It's just beautiful stuff, right? But like until there was highlight, you wouldn't think about it, right? The whole thing where you separate the schedule from it's brilliant. I mean, it's so clever. But like, what is the grand challenge that this fell out of? It's unclear, right? Again, okay, there's this very fuzzy thing of this is desirable, that is undesirable, but it's really how do you express what is desirable in a kind of convenient way? So yeah, I think it's very bottom up in my opinion, the at least
Yeah.
in my view.
Halide is a great example of what you said about like the defining the problem as being a huge amount of the work. And like I don't
Exactly.
want to take anything away from like the design or the compiler they made or anything, but like
Right.
just sort of identifying like the three forms of optimization they wanted to do and just and sort of like framing it this way.
Right.
That was the insight,
Exactly.
you know.
Just framing the problem was like, was just that was probably, yeah. So that's my
So
yeah.
we can maybe wrap up with questions about advising and advice for graduate students. So first of all, I mean, everyone should watch your influential talk on how to give a talk, right? I forgot what it's titled. It's
How to
a
design talks.
how
I
to
just gave
design
it at
talks,
Uppsala, so I reminded myself.
right? Yeah,
Yeah.
yeah. So like I guess how did you come up with that recipe? And maybe what is it for people who haven't seen the talk? I send it to all my students, so I yeah.
Okay, how did I come up with the recipe and how did I come up with what is the recipe? How did I come up with it, right?
Yeah,
So
yeah. What is the recipe? Like where does it come from?
So
Yeah.
at a high level, the recipe is, oh gosh, I should be able to distill into 60 seconds, right? At a high level, the recipe is you should think about your outline for the talk. So you should start with, again, it's actually a very type directed approach. I would say it's like very much motivated by the how to design programs, is you want to start with what is I want to achieve some goal, which to me is, I'm trying to write a function from input to output. The output is supposed to be whatever message, whatever clever idea, insight, whatever it is, right? And the input is the current state of the world, right? So I'm trying to take you from current state of the world, which is my input, to some output, which is here's my cunning solution and why it works. And now, just like when you have to write a function, like when you want to write a compiler, it's supposed to take in source code and it's supposed to produce as output x86. You don't do it all at once. You sort of break it up, right, into intermediate sort of steps. You parse it up into a syntax tree, and then you take the syntax tree and make it an IR, and so on and so forth, right? Various transforms on the IR, then finally you belch it out. In the same way, when you're designing your talk, you want to think about, well, first the input and the output, and then what are these intermediate blocks along these sort of road marks along the way? And then having designed the road marks, then you think about how you get from each road mark to the next, right? From each landmark, sorry, to the next. And you sort of, once you're at that level, the way you sort of typically do that is you try to come up with a compelling example that sort of illustrates, here you are at the current landmark, here's the next landmark, right? It sort of gradually builds up to the next landmark. And then I sort of have some advice on how what's on the individual slides. I would say the last sort of key invariant that I like to emphasize is that at any one point in time, the viewer, whoever's in the audience, they're looking at your screen. It should be totally obvious what they should be looking at. Like there should be like one central point of focus, and somehow you have to design your slide so it means so that they know exactly. There's 30 things on the screen at one point. That's overwhelming, and you really need to help people figure out what they should be looking at. So anyway, that's the short version, I think, Aus. How did I come up with this? That's a good point. I think I came up with this. Um, I suspect it was one of these things where we were talking about how, things sort of diverge and then converge. I think I came up with this because I saw this was maybe how I was, on the one hand, developing all my talks, and I thought this was a good way to do it. Two, it was when I was sort of advising students, I think this was the common mistake that people would make, is that there wouldn't be these kind of central sort of landmarks along the way, right? Where where yeah, I didn't know what am I supposed to be paying attention to? Like, why are you telling me this? What part of the. And then finally, it's like, look, it has this very kind of nice analogy to programming on the one hand, and frankly, to writing papers on the other hand too. Like when you're writing an introduction, again, or when you're writing a section, you want to sort of break it up into, these little pieces. Back when I was in grad school, my advisor was like, well, why don't you, here's the whole paper, the way you take a paper, you break it up into sections, you break each section up into sort of subsections, and then each subsection into paragraphs. And then the first line of each paragraph is like a type signature for that paragraph, roughly. It's supposed to tell you what that paragraph is about. And they should all sort of link up, right? And so I just thought it's a kind of natural progression into the talk, uh, whatever realm, as it were. Yeah. And so it was just like, okay, I'm saying the same thing like again and again. And I had to make a talk for PLMW. So like, I don't know. This is the one thing I can give advice on. I feel I have I feel enough convictions. Speak about this. That's how it came about.
So do you have like when you train your students to give talks, like do you train them by kind of osmosis or by like with deliberate practice? Like here's the recipe, come up with a talk, and let's analyze it, or
I have to say, I wish more of my students. I feel a little awkward kind of advertising my talk to my own students. So I think many of them have not seen it. Now, I can't be like, hey man, you should go to see my. I did recently one of Loris's students gave a practice talk and said, well, I think you should see my that because a lot of at this point I'm like, look, I have a bunch of feedback, but like 80% of that feedback is in those slides. So why don't you just go and see those slides so I don't
read
have
my book.
just read
Save both of us time.
yeah, save. But there's a fair bunch of there is a fair bunch of iteration. But I mean, for example, with my students, one of the things I tell them before they get started, I don't want to see slides. I just want to see like markdown text. I just want to see, here's these are the 5 segments, and I just want to see like a textual, because it's much easier to iterate on just raw text. You don't want to
Right.
be spending all this time fiddling around with colors and fonts and all that. Just like tell me what the little bits of pieces are. And then once we agree on that, then you can start making the slides.
Yeah, that
So
makes a lot of sense. Yeah. Yeah. Sometimes I feel bad when students like come up with a whole deck and I'm like, actually,
yeah, because I know that's happened enough times. Like, oh my gosh, you're gonna have to delete all of this. So I'm like, yeah, don't do that. Just show me this. And then once you have that and it's nailed down and you can sort of, work out all the dependencies and so on, how complicated the examples are, then go to town. And then editing the slides becomes a much more local and, a simple you really want to work out the global dependencies before you
Mhm.
commit too much to the actual rendering of the slides, in my opinion.
Yeah. Yeah. Yeah.
very much the virtues of the waterfall development model, where like the cost of bugs goes up later in the development pipeline.
Exactly so. That's exactly right. It's the same, exactly the same principle at work.
Okay. Well, we have maybe the hardest question for you that we saved for last, which is, do you have any advice for young researchers? So you can pick your definition of young researchers, but do you have anything you would like to pass on if people are entering any kind of a CS field?
The facetious advice is you should not listen to get advice from old people like me. That's all. Take any advice from people like me with a grain of salt. That being said, I would say the two things I would say are, one, especially if you're an undergrad, but even if you're in graduate school, you can never have learned enough math. So you should just like take more math if you can. I always feel bad that this is my personal regret, is that I never understood linear algebra. Just like, and I feel at this point the ship has sailed. My wife tells me otherwise. She's like, no, you can still be saved. I'm like, I don't know. So I never really got linear algebra, and for whatever reason, I feel bad about it, right? So I would say take as much math as you can, because it's just a useful thing to do. Two, I would say you should. I think this is my theory. I mean, if you people who studied psychology will sort of know this, is that the older you get, I think the fewer the set of things that are interesting, that are really interesting to you. So you should try to fight this for as long as you can. So try to be as interested in as many things for as long as possible. Because don't just say, oh, I like mumble and I don't like mumble. So just try to like as many things for as long as possible, because you never know. And three, I would say, if you're doing research, you should I should say you should find like a Rupak-like character. It's if you're doing research, it's yeah, don't worry about like credit and all of that. It's just much easier and just much more fun. It's if you're working with other people, it's just much more fun. So that's what I would say. Is these are the three things. Try to be as interested in as many things for as long as you can, because that just age will naturally winnow this down. So just try to fight that, and and try to just work with fun people.
Well, this has
I like
been
that
incredibly fun.
Well,
Yeah,
yeah, it's
thank
been
you.
a real pleasure. It's been
Yeah,
a real pleasure. Thanks, Aus and Adrian.
yeah, it's
That's
been
awesome.
good.